All right, good afternoon. So, today we're talking about multi-level page tables. They're like single-level page tables, except more fun. So first off, it's like, I guess, after the midterm season, so hopefully, since I'm new here, people can give me some feedback since there's probably lots of stuff I can improve. Yep.
I have feedback. Can you have a shorter link, please?
A what?
A shorter link, please.
It's clickable. Just download the slides. Yeah, so download the slides, click the link. That apparently was the shortest link Google would give me, but I could have done another one. It's posted on Discord too. Yeah, it's posted on Discord. It's clickable if you download the slides, and yeah, that would be much appreciated since I am brand new. Okay, so today also, and it's after like the quizzes and the labs, so there's separate sections to give feedback on the labs because I know they're a bit not terribly great. So there's like a lecture half and then a lab half and then like a free form. So today though, we're talking about page tables and multi-level page tables and how they can save some space for sparse allocations. Because as we were talking about, even with a 39-bit virtual address, if we have a single level page table, each process could have a gigabyte page table, which is not great, not going to work. Yeah.
Wait, I don't get how it could have a gigabyte page table. I'm confused by that.
So if we have a 39-bit virtual address and our page size is 4,000 whatever, that means that there have to be, what is that? 39 minus 12, 21 entries? Or no, more than that. All right, let's go. So, okay, that doesn't work. Great, thank you. So, if we have a 39-bit virtual address, well then, we'll have 12 bits for the offset, and then we would have 27 bits for the remaining, right? So, and then, so there'd be to the 27 entries that we'd have to compute. And if each entry, so you'd be given the size of an entry. Each entry would be 8 bytes, so it'd be the same as 2 to the power of 3. So that is equal to 2 to the power of 30, which is a gigabyte. So it would take a gigabyte if we have a big page table. Okay, I really wish this worked. Okay. So this is what we're going to do to save space. The trick here is to make each smaller page table fit exactly on a page, and then they just and then an L2 page table would just point to an L1 page table, which would then point to an L0 page table, and then we'd translate the address just straight up from there, just replacing the virtual page number with the physical page number from the L0 page table to give us a physical address from that virtual address. So we'll walk through it. Yep.
What is the EXT?
Sorry?
Yeah, EXT.
Oh, EXT, it's just extension. So some bits we don't use because this is use space for a 64-bit address, and this is only using 39.
Okay.
So it's just extended use that you can use later. So if you want, you can have more levels of page tables and have like a 4th level if you want and support more virtual addresses. Yep.
What's a sparse allocation?
So sparse allocation just means that, so with a normal single level page table, you have room to allocate everything. So you could have an entry for everything. For sparse allocations, it means like you can only use like 1 or 2 pages at a time. So if you only use 1 or 2 pages at a time, you don't need a massive table that's mostly empty. So sparse just means there's not that many allocations. So for RISC-V, you want each level to occupy 1 page. So if we know the size of a page and the size of a page table entry, you can figure out how many entries can fit on a single page. So in this case, the page size would be 4096, so 2 to the 12, and each of the entries are 8 bytes, so 2 to the 3, so we can have 2 to the 9 entries on each page. Make sense for everyone? So then the page table entry, if you're in like ln, it just points to the next lower level page table, ln minus 1, until you eventually get to L0, and then that's your translation. And we'll see an example of that. So you just keep on following them down the levels until L0, and then that's your translation there. Yep.
Why is each entry 8 bytes again?
That will just be told to you. So if it's a 64-bit machine, it'll be 8 bytes. So we'll see an example where we do a 32-bit machine, so they're going to be 4 bytes. So you can fit more entries. Okay, so this is how you do a translation with just 1 additional level. So we'll just consider 1 virtual address, which is 3FFFFF008, which if you write it out in binary, it is this. Or if you separate it out for our L1 index, it would be the 9 top bits. So it'd be 11111111, and then the next 9 bits are 11111111, and then the last 12 bits, which correspond to the offset, is 0000, and then 1000. So this is a 30-bit virtual address, so we're just using 2 levels of page table. So if this was only a single level page table and we were supporting a 30-bit virtual address, then our single page table would be 2 megabytes. So it would be 30 minus 12. So we'd have 2 to the 18 entries there, and each entry would be 2 to the 3. So that means if we had a single page table for a 30-bit address translation, then it would be 2 megabytes. Everyone good with that? So back to lecture, but the previous lecture, but if we only had 30 bits. So if we had a single level page table, it would be 2 megabytes, but to just map a single page, because you need a whole page table. But in this case, if we have multiple levels of page tables, then you only need 1 page for the L1 table, and then 1 page for the L0 table. So in total, you only need 8 kilobytes for the page tables instead of a whole 2 megabytes. And in the worst case, this scheme would actually consume more memory than if you had a single page table, if you had to record every single entry, because you'd have an L1 page table with 512 L0 page tables, which would waste up 2 megabytes plus the L1 page table. So let's see that quick. So again, here's what we're considering a 30-bit virtual address, and we'd be given the page size 4 kilobytes. So for a single page table, we need 2 megabytes. So it would be the number of virtual pages, which in that case, our page size is 2 to the 12. Whoops, page size. And then we'd have up to 2 to the 30 addresses in this. So that would be 2 to the 18 entries we would need. So if we have 2 to the 18 entries, it's the number of virtual pages we need to keep track of. And our page table entry size would be 8 bytes. So that's where we get our 2 megabytes. So this is 2 megabytes. And I write MIB because it's megabytes or some weird way to say that. It basically just means it's always power of 2. If it's megabytes, whether it's power of 2 or 1,000, it is up to whoever is marketing the thing. So, but if you read MIB, it's like power of 2 and you know what it's saying. So we have that big address, which was 3FFFFFFFF and then 008. So I'll just write the hex offset here as hex. So those are the 12 lower bits. So those are the offset that we don't have to translate. So then the rest of them are index bits for 9. So your first L1 index here would be 11111, which is the same as 511. So remember, when you're translating these addresses, you start off with a root page table, which would be the highest level. So your program would initially point to a L1 page table. So in order for this to actually translate well, let's assume that the root page table is at address 7,000, so it has to be aligned to a page. So it would be at 11,000, and then the page table itself would have 2 to the 9 entries, which would be 0 all the way to 511. And then, since this is a page table, one of the things it would have is the physical page number that corresponds to that entry. So for this, the entry for 511 could be something like just 8. So if it's 8, and then what else would be in the page table entry? Yeah, there's some flags. If it is one of the things that the hardware would need to actually follow the page tables as a valid bit. So there'd probably be a valid bit here to say that, hey, this entry is valid. So since everything's aligned to a page, in this one, the L1 index was 511, so it would go look up that in the L1 page table. In this case, it would show that, hey, this is actually pointing to physical page number 8. So we would look up another page table, and the address of this page table would start at 8,000 because it's aligned at a page. So now this would be our L0 page table. So in the L0 page table, there again would be the same number of entries. So in this case, it could have a physical page number of something like CAFE and be valid. In that case, this is an L0. If we look up our index from the address, it was 511 as well. So since this is an L0 table, we can just directly translate it. So what would our virtual address be? What would our physical address be that we're translating from this virtual address? Yep. Yeah, so the offset would stay the same because it's within a page. So our physical address, we followed it all the way to L0. So we just plop that in for the physical page number, CAFE, and then the offset was 008. Yep.
How does following page tables down save space? It just seems like it takes more time because rather than immediately getting it, you have to
Yeah, so the question is, how does that save space? So each of these smaller page tables, they fit on a page. So this takes up 2 pages. And if we had a single big page table, it would be 2 megabytes.
Okay.
Because,
If you had like to the 18.
yeah, so this is 2 levels. So the 9 bits are here and then 9 bits are here. So if we just had one big table, our index would be 18 bits, right? So if we have 18 bits, that means we would have 2 to the 18 entries times 2 to the 3, which is the page table entry size.
That's the PPN, right?
Sorry?
That's like the PPN size, right? Like counting size.
Yeah, so page table entry size is going to have, inside the page table entry is going to be the PPN and flags.
Okay, and that combined is 2 to the power 3.
Yeah. Yeah, so this would be 2 megabytes. Yep.
So for the L1 table, when you have 0x8 as the ppm, does that represent 0x8000 or?
So this, since it's a physical page number, you assume that everything's page aligned. So those like 3 hex characters would be 000. So that's why if it's 8 here, that's physical page number 8, because whenever we translate addresses, we never touch the offset. Yep,
So how many L0 tables are there?
as many as you need.
So we allocate them along the way, sort of?
Yeah,
As we need them?
yep. Yeah, so this is why it saves, because you just have as many L0 tables as you need.
Okay, so how do we reach like this 8,000 from that 8? Like, why is the offset 000 and not 008?
For this,
Yeah.
so this corresponds to the next level of page table, and you don't know what index you're even going to be accessing. So you assume it's aligned to a page, and then you use the index from the address here, which could be anywhere on that page. It wouldn't correspond to 008, the index. So because it's aligned on a page, fits on a page, you know where to access everything. So if it's index 0, it's the first one. If it's index 1, it's byte 4, and so on and so forth. Yeah.
But if the whole process to get your physical address, doesn't it seem like to get from the L1 to L0, don't we need to know the actual physical address of like where L1's pointing, so L0, where L0 is, to like access that data?
Yeah, so L0 is going to have to be allocated somewhere.
Okay, so that's like globally known or something like that.
Yeah, you're the operating system. You can do what you want.
Okay, I see.
Yeah.
Wait, I'm still a bit confused. So what does the ppm stand for in this case, like for the 0x8?
Physical page number. So, which just says, in the case where it's pointing to a lower level, it's telling you the physical page number that that lower level page table is on.
So in this case, it's why is it on 511?
So 511 is the index from the virtual address. So when we had, So when we had here, our virtual address was 3FFFFF008. So if we divide that and go back one, so here it only goes up to L1. So this is the number of index bits for L1 and then the number of index bits for L0. So that's where they came from. Yeah.
How can it tell when the result of the query from like L1? How would it tell when the next pointer is to another page table and not to the physical address itself?
So you would have to, the hardware would have to know how many levels are set up. So these are different modes. So in this case, it would be like the 39-bit mode, which knows it needs 3 levels. If you wanted to have a 30-bit one, which it doesn't support, it would know that follow only 2 levels of page tables, and you would have to set it up. Yeah.
Oh, so essentially that 0x8 is the physical address of the L0 page.
Yes.
Okay.
Yeah. Yeah. 08 is the physical address where that L0 page table is. Yeah.
So is the physical address only stored in the L0 table?
Yeah. The page tables will only have physical addresses in them.
So the lowest level L1. So are all of physical address stored here, or some part is stored in this page table and some part is stored in another page table?
Yeah. So all the, like in this case, all the L1 physical page numbers, they're going to correspond to still physical memory, but it's going to be the physical memory where another page table is. And it's all going to be in physical memory because the kernel's managing that. So the kernel is managing all the physical memory.
So the numbers in the L0 table directly tell us where the physical address is, right?
Yeah, all of them will tell you exactly where the physical address is.
So we only have 512 physical address.
Well, it's 512 that point to another page table that you can have, 512 of that point to another 512. So it's like exponential, right? It's like a big tree, so you can support the same number of addresses. Yeah.
So fundamentally, in like the worst case, you're still allocating the same amount of memory, like size. It's just that like if you only needed a smaller like amount.
Yeah, in the worst case, you're actually using more memory.
Okay.
So in the worst case, where you have to have an entry for every single thing, all of your L0 page tables would be full. So you'd have 512 of them, which is 8 megabytes by itself.
Right.
And then you'd have one L1 page table to point to all of those.
Right.
So you'd waste an additional page if everything's full,
I see.
which would get even worse if you had 3 levels.
Right.
So you'd have, 512 times 512 L1s or L0s. Yeah.
But in general, since we don't usually allocate all of them, it's usually fine.
Yeah, unless you're Visual Studio Code, you don't use like gigabytes of memory. Yeah.
So how would it know that you're at L0? Is it just something we just design to the?
Yeah, the MMU would know what mode it's in, and you as a kernel have to make sure that your page table points to a lower level one and a lower level one, and it knows that it only goes 3 deep in that case. Yeah.
So how is the address of the lower level table exactly determined, like the offset at the end?
The offset at the end?
Like in that example, it's 8000. So if the address of L1 was 7001, would that be 8001?
For which one, sorry?
For this one here, so we have 0x8 at ppm, and then we say that
Yeah.
L0 is at 8000. So
Yeah.
where does that 000 exactly come from?
So this 000 here?
Yeah.
So it comes from the fact that all the page tables are going to be aligned to a page. So if they're
12 bits, right?
yeah, 12 bits, which is 3 zeros in hex. So they're all aligned to a page. Otherwise, if they're not aligned to a page, then it's like, oh, well, where do I start? How do I access whatever index it's at? It just becomes a giant mess. So if everything's fits on a page and is aligned to a page, if you're the kernel, you only have to deal with pages, and everything past that is fairly easy. And essentially, if I do this translation and have this all set up, well, if I want to translate the address, so say I'm accessing like the next instruction that has an offset of 009, I mean, it's going to do the exact same translation, go through all of it, and the physical address at the end of it is going to be CAFE009. And I'm not going to have to do new page table entries or anything like that. So they're all going to be the same entry. Yep. Yeah, so well, the kernel is going to try and minimize the number of tables there are, so it will give you, that's why it gives you virtual addresses sequentially, like your heap starts from the top and goes down. So they're all going to be beside each other in these page tables. So it's going to give you sequential virtual addresses to make this as small as possible. Yeah.
So every single process has its own L1 and its own L0s, right?
Yeah. And there's only one root, so if there's two levels of page table, you'll have an L1 and an L0. So you'll only have one L0, so that's the pointer that changes when it changes processes. But if you have three levels where you have an L2, an L1, and an L0, you'll have one L2, and that's the pointer that changes.
Wait, sorry. Why does the L2? So the L2 page table is the same for all processes?
No, it changes. So that's your root page table.
Oh, I see. Okay.
Yeah.
And then what's SATP?
SATP is the RISC-V name for the root page table. It stands for Supervisor Address Translation and Protection. It's a very good name. Okay, so we did that. So that was our example where we had one L1 page table with the entry index 1511 with a physical page number 888. So that means since all the page tables are aligned at a page, that there's an L1 page table located at 8000, and then it would have some entries in it. Hopefully it would have the entry for 511 with CAFE, and it would be valid. In that case, the physical address would be CAFE 008. Mm-hmm.
So if it's not valid, would it just be a page fault?
Yeah, if it's not valid, it's going to be a page fault. And in that case, in your user process, you'll get a seg fault. But we all know that seg fault name's just silly because segmentations don't exist anymore. Yeah.
The ppn in the L1 table has 12 bits, but ppn in L0 table has 16 bits, right?
In this case, the physical page number would be as much as there are in that entry. So there's just a lot of leading zeros. In this case, if it is a 56-bit physical address, there would be 44 bits in there. But all the leading ones are 0. Yeah.
How does the OS ensure that for the L0s, it never gives like the final physical address to be the same across like all of its many processes that it's running?
So if you're the kernel and you don't want to make sure that you give the same virtual address to 2 or more processes,
No, like the same physical, like
they're the same physical address.
you never want to map the same virtual, or it doesn't matter, but you never want to map a virtual address to the same physical address in across processes, right? Because you want to make sure that they have the same different physical memory.
Depends, but
In general.
yeah, in general. But so you want to make sure that you don't map the same page to 2 different processes.
Yeah.
So you have to keep track of, we'll go into that. If you're the kernel and you're allocating memory, you allocate it in terms of pages. So you map it, and then you say it's used, so you don't give it to anything else.
Okay, so do you just have like a large array and you just run through it every single time to find one that's empty?
We'll talk, that's next, I think. Yeah, so processes use a register like SATP, which was that stupid acronym, to set the root page table for your process. And then after that, the MMU is going to use that page table to go and do add the virtual address to physical address translation. And there's a good comment too of like, isn't this slow? Where I have to access memory again, to maybe access memory again, and then I get my physical memory where my information is actually. And that's a good comment. It is slow. But first, talk about the page allocation. So it can just, the kernel only allocates in things of a page, so it's actually really easy. You just have a free list of pages. So if you have, when the kernel boots up, it knows how much physical memory there are. it would just divide the physical memory into pages and maintain a free list. So on every single page, it would just write out a pointer to the next one as part of the initialization process. So it only needs to write a pointer every like 4 kilobytes. So it could do that fairly fast. And then you have a linked list of your entire memory. And then whenever, so then these are all unused, so we'll just have some pointer to the next free one, and that happens at boot. And then whenever you need to grab a page, you just look at the first page in your free list. So you just look at the first page in your free list, you map it, and then it's not free anymore. Yep.
Does modern Linux still do this?
Yep. Yeah, kernels, so memory allocation, like your malloc and stuff like that, that actually cares about different sizes, that the kernel doesn't care. So
Is it the entire blocking? You deal with it, and malloc deals with it?
yeah, malloc deals with it. So malloc will only allocate heap, so it will just make the heap bigger, and the kernel does that in terms of just backing it with pages. And then malloc figures out how to give you your 8 bytes or whatever you need. So a fun lab is so malloc and that's all user space. Fun lab you could do that, I guess, is in this course, is you could write your own malloc. Because the kernel doesn't really care. It just gives you heap and then says you manage the heap. So
System call then to get more memory.
yep, there's a system call to increase the size of your heap, but that's it. And it only does it in terms of pages. Sorry? You can decrease, but it's going to be hard because you have to have the bottom page filled to be able to decrease it. Or sorry, you have to have the bottom page free to be able to decrease it. So if there's still an allocation alive that's like in the middle or somewhere, you can't free pages. Yeah.
So this is only makes it fast to like figure out what's the next free physical page, but like
Yeah.
you still have to follow through the whole chain to get from virtual to physical, right?
No.
Why not?
For what? Why would you have to follow the chain?
Like this would be like when the kernel is trying to put it into the page table, right?
Yeah, when the kernel is going to put it into the page table, the free list has a pointer to the next free one, so it just picks that one. That's the next page.
Right, but when you're trying to convert the virtual address to the physical, you still need to go through L1 or L2, then L1, then L0, right?
So it would just grab that page and then it would be an entry in the table.
Right. Oh, so you're just saying it's not super slow because it's only like 3 linked list elements or something like that.
Yeah, it just picks off the head of the list and says, hey, it's not there anymore, and fills in that entry. So if you need to back some memory, you'd eventually get to L0 and you need to grab a page to correspond to that. If there's not, you'd grab it from the free list. That's really quick. You'd grab it from the top of the head. You would populate that entry in your L0 page table, and then you're done. Then if you need to allocate it, it's also really easy if you're the kernel, because you know what it maps to. So you just say, hey, you're not valid anymore, so then it wouldn't translate it anymore, and then you can add it back to the free list. So you just get your page back. So and allocating and deallocating pages is really, really easy. So the kernel can do that pretty easy. And yeah, user space allocation is a lot harder, and we'll talk about user space allocation later. But the kernel gets it easy. It just cares about pages. So here's where, using page tables for every memory access is going to be really slow because we have to follow pointers across multiple levels of page tables. And likely you also use the same page multiple times. So if you think of your C program, your stack would be on a page. So if you use one element on your stack, you're probably going to use the next element on the stack and then the one after that. So why would you bother translating the same thing that translates to the same physical page number 1,000 times when you know you're going to use it over and over again? And also some processes might only need a few virtual page number to physical page number mappings. So we just pull out the classic solution and throw a cache on it. So the cache for your MMU is called a TLB, or translation look-aside buffer. The image kind of sucks, but basically all it is there's a logical address up here, which is the same as virtual, and then there is a cache. So it will check the virtual page number, see if it's in the cache, which is that ugly thing in the middle, and then it would have the page number to frame number, which is just the physical page number. Again, this is where the terminology gets weird between people. And if it's in the cache, it just gives you that address back, and then you have your physical address so you can access the memory. If it's a miss, then you have to go through that page table thing of going through, if there's 3 levels of page tables, you have to go through L2, L1, L0, and then the memory access. So remember, one of our goals was to make things really, really quick and make it appear that using virtual memory is just as fast as physical memory. So since there's a cache, we can calculate whatever our effective access time is. So in this case, we could assume a single page table. So there's only one additional memory access if we miss. So the TLB hit time is if it's in our cache. So it will take a small amount of time to check if it is actually in our cache. So the time for a memory access, if we have an entry in the cache, is the amount of time it takes to search the cache and get it from it, plus the time of the initial memory access itself. And then if there's a miss, well, we still had to search the cache, and then in this case, we had to do 2 memory accesses. So if there's only one level of page table, we had to look up the page table, find wherever that physical memory was, and then go ahead and do the original access as well. So if I had 3 levels of page table, what would that be? Yeah. Why 3?
Doesn't it just have to access the first one, and then that one next to the second one, that one next to the third?
Yeah.
Oh, then 4.
And 4. Yeah. So you need, if there were 3 levels of page table, there'd be 4 memory accesses. So 1 for each level of page table and your initial access. So it gets really bad the more levels you have, which is why on a 64-bit machine, we only have a 39-bit virtual address, because it's good enough. And if we added another level, it would be another level and it would be slower. Yeah.
So, like, it's impossible to have a process that requires more memory than the 39 bits would need, right? The initial process.
Currently, yeah. But you can switch the mode on it. So that's like the default mode of 39-bit. On RISC-V processors, you can do 48 or 47-bit is supported. So, and you're not going to get more than 47 bits of memory right now. Okay, and then to calculate your effective access time, or your EAT, it is alpha, and alpha is just the proportion of cache hits. So it's the proportion of hits times the time for a hit, plus 1 minus alpha, which is your miss ratio, times the amount of time it takes for a miss. So if you assume alpha is like 80% hits, and your search time is 10 nanoseconds, and your memory access is 100 nanoseconds, well then our effective access time would be 0.8 times 110 for our search and our memory access, plus 20% of the time we'd have to take 2 memory accesses and the search. So our effective access time in this case would be 130 nanoseconds, or like 30% slower than it would be if we just used physical memory, which isn't great, but it is way better than just having virtual memory without this cache, because all of our accesses would be 200 nanoseconds in that case. And realistically, if we had a 3-level page table, they would all be 400 nanoseconds, which would be 4 times as slow. So instead of being like 4 times as slow, we're like 30% as slow. So now too, there is a problem with this cache whenever we're switching processes. So if we switch processes and we don't do anything with the cache, well, if the new process that got context switched in happens to use the same virtual address and we don't do anything with the cache, it would be a cache hit, and then it would map to the old process's memory. and then it could monkey around with that and bad things could happen. So the simplest thing you can do is just invalidate the cache whenever you context switch so that it has to recalculate the virtual address for the new process, which would work, and it's a bit slow. Some implementations, if hardware developers are nice to you, in your TLB, you can tag entries with a process ID to make them unique. So you would tag a process ID with the virtual address so that when you context switch in and your new process happens to use the same virtual address, it would have a new process ID, so it wouldn't actually get the result of the last process. So that's in some hardware, but not really. For RISC-V, you have to explicitly flush the cache with that sfence instruction. On x86, if you change the root page table pointer, it automatically flushes the cache for you. So you don't have to worry about it. So another question too is, how many levels of page tables do I need? So it depends on the size of your virtual address. So here's an example for pre-2000 era when we had 32-bit processors. So if we have a 32-bit virtual address and our page size of 4096, well, since we're on a 32-bit machine, our page table entry is only 4 bytes now because we have less memory. It's only a 32-byte machine. So we actually have more room for entries on a single page. So again, we want all of our lower level, or all of our page tables to fit exactly on a page. So in this case, we can fit 2 to the 10 page table entries on a page. So each page is 2 to the 12. And now the page table entry is 2 to the 2 instead of 2 to the 3. So we can fit 2 to the 10 entries now. So the number of bits you need to index into the page is just like the log 2 of the number of page table entries per page, which would be 10. So in this case, the number of levels we need is, there's a round up of ceiling. So the number of virtual bits minus offset bits. So in this case, it would be 32 minus 12 because that's our page size. So, which would be 20 divided by the number of index bits we need for each page table. So in this case, it would be 10. So 20 divided by 10 is 2. Nice even number. We don't have to round up. So we need 2 levels. But in this case, if it was a 33-bit virtual address, then we'd have 21 divided by 10, which would be 2.1. So we'd have to round up, and we'd need a 3rd level of page tables, which of course would make everything slower. Okay, so to see that the TLB is actually a thing, there is this fun little tool written by Linus Torvalds himself. So he wrote this, so it's definitely correct. It gives you 2 arguments. It will do an allocation of size, and then access that memory every stride bytes. So if its stride is 4, it's going to access every 4 bytes. So byte 0, 4, 8, 12, 16, so on. So let's go ahead and see that. So knowing what we know about the TLB, why doesn't this work anymore? So knowing what we know about the TLB, whoops. If we do this, well, we would allocate ourselves a page and then access every 4 bytes. So if we do this, this should be relatively fast. Why would this be really fast or relatively fast? Yeah.
It's all on the same page.
Yeah.
That page got cached.
Yeah, so it's all on the same page, and that page would get cached. So we allocated 4096 bytes, and we accessed every 4. So if we do that, we access memory 1024 times. So since they're on the same page, the first time we tried to access memory, it wouldn't be in the cache. So we'd have to follow the page tables and then do that. But then after that, since everything's on the same page, they'd all be cache hits. So it'd be fast. So on the flip side, if I allocate 512 megabytes and then access memory every page, this should be really, really slow. Yeah.
So because you're not using malloc, you're able to allocate that much, or in a regular C program, can you allocate that much memory?
Depends on the malloc implementation. For that bank example I had, I allocated like this much memory, and it was like, yeah, no problem. And then, yeah, when I tried to access it, it crashed.
But it's not going to crash here.
No.
And like, so what's the difference then? What are you doing making this okay, the other one not?
So I actually have enough RAM to do this.
Oh, okay.
The other one, it just kind of lied. But if I increase this a lot more, it would crash the same way. So if I do this, this is essentially no cache hits. So I'm accessing every page. So every single time I go through, it's going to have to go through all the page tables, look it up, and it is dog slow. So it is 40 nanoseconds instead of like under 2. So this does have a big effect, and this is also why you want to keep things as close as possible. So if we do this, one where we allocate 16 megabytes and access every 128, well, it should be somewhere in between. So if we run that, get 11 nanoseconds, which isn't great. And that's because, well, within the same page, we're doing 32 accesses. So the first access is a miss. So we'll miss once, and then we'll have 31 hits in a row. And then miss 31 hits, miss 31 hits.
And they're all the same number of total accesses, though, right?
So it depends on the size for the number of total accesses.
No, but like in these examples, I mean, you're all doing 1,024 accesses to memory, right?
1,024. So the number of accesses is just, oh, I can't copy and paste. The number of accesses is just side divided by stride. So I don't think they're all the same.
But that would also affect it, no?
It's just how many measurements you take. So it just takes the average of them.
Okay.
So yeah. So more measurements, the more consistent your number would be, but it'd be about the same.
Oh, so it's taking the average of your, that's what it's doing.
Yeah, it's taking the average.
Oh, I thought it was like it runs the test and calculates afterwards how long that took.
No, this is the average time for memory accesses.
Okay.
Because 40 nanoseconds is really, really fast. Okay, so
Wait, so what was the smallest one? How many cycles was it?
cycles. So the smallest one was 6.6 cycles. And this was on my machine, so I ran it again, and it's a bit different. So you can see it makes a vast difference. So this is where the kernel only cares about. So that's that sbreak instruction that just makes the heap bigger. So it would grow or shrink the heap, and that's it. Your stack has a set limit. It would be like 8 megabytes. So for growing, the kernel just grabs pages for you from a free list. To fulfill it, the kernel would set the page table entry valid, do the mapping for you. And then in memory allocators, this interface sucks because you generally can never free memory again, because you need to free the last allocated page, and you'd have to make sure that that's not being used anymore. And in general, that's not going to happen. It'll just stay claimed by the process and waste memory. But if you remember memory allocator, a fun other system call you can make is called mmap. So that can bring in large blocks of memory at a time, and then you can go ahead and free them because they'll be backed by pages. So if you use a page and you're not using that page anymore, you can go ahead and free it.
So how does sbreak return? Like, does it give you, like in the code itself, like it adds an extra page to your heap, but like.
Sbreak itself just tells you the new address of your heap, like the new bottom address.
The new bottom address.
Yeah. Yeah, if you call sbreak, I guess we don't do a lab on it, but if you call sbreak with null, it tells you where the top is, and then you can set the bottom with an argument.
Okay.
So then you know how big it is. So if you're malloc, you're the one that makes those calls, and you manage the heap. And yeah, so kernel initializes all that. This we saw before, I'll wrap up quick. So it would also put like a guard page at your stack that doesn't map to anything that would make sure it invalid. So instead of running through your stack and changing some random data, instead it would generate a page fault and then kill your program so it doesn't just do wacky stuff. So that's fun stuff you can do when you control pages. Yeah. Yeah. We don't see that. That's for more advanced courses. You don't have to worry about a trampoline yet. The kernel can also do more fun stuff with virtual addresses, so it can eliminate some system calls by just mapping memory. So like clock get time won't do a system call. It just maps in virtual memory that lets you read that value directly, and you don't have to do a system call, so it's nice and fast, especially when you have like a nanosecond timer. And yeah, page faults let the operating system do all that copy and write stuff. I'll lazily allocate pages, which is why it lets you allocate more memory than you have and then crash whenever you try and use it. Or do fun stuff like swapping that we'll see later. So we saw page tables translate the addresses. Single large is wasteful. Multi-levels save space for sparse allocations, but slower. Kernel allocates from a free list, and then the TLB speeds up that slow process. So yeah, that's pretty much it. So if you want, let me know, and I can like do an example program of this, and we can set up page tables ourselves if it doesn't quite make sense, because sometimes this is confusing. All right, well, with that, have a good one, and I'm pulling for you.